All right, this is the last example for comparing linear, exponential, and quadratic functions. So example 6 says, each year a team of researchers counts the number of sea turtle nests on an island and in a coastal wildlife refuge. The function L of x, which is quadratic here, the function L of x represents the number of sea turtle nests counted on the island, x years after 1990. All right, so we need to make sure we remember it says after years 1990. So 1990 is kind of like your original, that's your starting point. That's your original year that we're going to look at. So in the wildlife refuge, the team counted 1,275 nests in 1990. Again, that's the starting point, and observed that the number of nests increased by 6% each year. A part says from 1990 to 2010, which location had a greater average rate of change? B part says which location will eventually have a greater number of nests. All right, so we're only going to look at part A for now, so we need to find the average rate of change for two functions. So the first one is L of x, that's given, and the second one tells us that at the starting year, they have 1,275 nests, but it increases by 6% each year. So if you remember, when we're talking about increasing by 1% each year, that's going to be exponential. All right, so that's an exponential function. All right, so we can call this, because this is the refuge, let's just use R of x. And we know that it's going to be A times B raised to a power, but we also can extend that a little bit further. Remember, we can do A times. This is increasing, so we know it's exponential to exponential growth, so we can do A times 1 plus R, our rate, raised to the t, which is time. So that's kind of a little bit more specific to this problem. So if we do that, we know the starting amount is 1,275. And 1 plus our interest rate, so remember 6% is equal to 0.06. So it's going to be 1.06. That represents the 6%. And then times t. All right, so to find the average rate of change from years 1990 to 2010, from 1990 to 2010, that's 20 years. So we're going to have to put in a 20. I don't know why I wrote a 0 there. That's a 5. All right, so I've got 1,275 times 1.06 raised to the 20. All right, we know if we put in our calculator here, we can find what that number is. So let's pull this up and see. All right, so I've got 1,275 times 1.06 raised to the 20th power, because we're looking at year 20. And if we do that, we get 4,089, approximately 4,089. So that's 4,089. We know the original year there was 1,275, so we can use our starting point and year 20 there for that. We need to do the same thing for L of x. So remember, L of x represents the number of sea turtles on the island. So we're going to say L of x equals 4x squared plus 72x plus 1750. And we need to figure out what the number is after 20 years. So from 1990 to 2010, again, is 20 years. So we're going to have to plug in that number. So we're going to do 4 times 20 squared plus 72 times 20 plus 1750. All right, and using our calculator again, let's see what that value is. Let's see if I can type it all in at one time. So 4 times 20 squared plus 72 times 20, and then plus 1750. And that's 4,790. So that one's 4,790. All right, and again, we know that the original amount here, the y-intercept, 1750. All right, so we have to find the average rate of change of both. All right, I've slid the pictures up out of the way so we have a little bit more room here. So let's say we have average rate of change for R of x. Okay, R of x, we had 1489 minus, and remember, initially we started, the first year there was 1275. So 1275. And then we started with 1990 and went to 2010. So if we subtract 1990 from 2010, that's going to put us over 20. So that's just 20 years. So we don't have to do, I mean, we can put in 2010 minus 1990, but if we go ahead and subtract and put 20, that's fine as well. Just kind of simplifying a little quicker. So 4,089 minus 1275 would be 2814 divided by 20, and that is about 141. All right, so what did I do? I did R of x first. So this is R of x, average rate of change for R of x. And then I'm going to do the average rate of change for L of x, which is the island. All right, so this is L of x, average rate of change. And it's going to be 4,790 minus the initial value, which was the 1750, because that's the y-intercept. We know that's the initial value when it's a quadratic function. And then again, we did 2010 minus 1990, again gives us 20 years. Now, if I do 4,790 minus 1750, I get 3,040 over 20. So all I did was subtract here. I'm still dividing by 20, and that's going to be about 152. All right, so I've got 152, 141. So again, R of x is the refuge. L of x is the island. Okay, so the average rate of change here is about 141. And the average rate of change here is about 152. So we can conclude, since L of x is 152, that's greater than R of x, which is 141. We know that L of x represents the island. So we can say the average rate of change was greater during 1990 and 2010 for the island. But we also can say, for part B, it says which location will eventually have a greater number of nests. So we know from definitions and everything and all the things that we've looked at, we know that if you have an exponential function, it will eventually pass up linear and quadratic functions. So since we're comparing a quadratic function with an exponential function, even though at this point after 20 years, this number is greater, we know that eventually the average rate of change for the refuge will pass up the average rate of change for the island. So if we wanted to see that, we could graph it. So let's use our graphing calculator to put these two functions in and graph them. So I've got 1275. Make sure you type it in correctly. 1275 times 1.06 raised to the x power. All right, and then our second equation is 4x squared plus 72x plus 1750. And then if I hit graph, it should graph both of those equations. But remember, my table of values is, right now I've only got this set at a 10 by 10. This y-intercept is 1750. So I know that it's not even at a starting place where you're going to see this unless you change the window. So let's change the window. I really only need quadrant 1. So I don't need many of my negative values here. So let's change this to -2. Can't be a positive number. Your minimum has to be positive. X, let's change that up to, say, 40. And then our y values. And again, sometimes this is just a guess. I'm just kind of trying to make sure I can see my two functions on the calculator screen. So when I go to a maximum value, I know I'm going to have to go really large on this because I'm looking for a value when they cross, and we've already looked at 20 years of time, so we're going to have to go past that. So let's go to let's try 1,000. All right, looks like it is still, oh, well, I don't know why I tried 1,000. The y-intercept is 1750, so I'm going to have to go a lot larger than that. So let's go back to window. Oh. Let's put in 8,000. I'm going to jump up there. All right, and our scale, we can go by, let's go by 100. All right. All right, so now we're seeing one function. That's our exponential function. You can tell by the shape of the curve. Well, actually, at this point, if you're only looking at one quadrant, they kind of both look the same. So go back to y equals. So the blue line here, you can see on the graphing calculator, the blue line is exponential. The red is your quadratic. So blue is exponential, red is quadratic. So you can see at some point here, they're going to intersect. All right. And then after the intersection point, you can see that the blue line is going to get steeper or grow faster. So the red, the quadratic function, is going to be greater for a little while, but then the blue line takes over. So let's see where that location is. Let's do second trace and intersect, which is 5. I'm going to have to hurry. I'm about to run out of time here. All right, so I'm going to get close to that intersection and hit enter. And then you have to go up past the intersection and hit enter again. It's going to guess. You hit enter again, and it says at the intersection 31.46 and y equals 7,975. That's when they intersect. And after that point, that's when the exponential equation will then be greater or grow faster at that point. So using the calculator, we just used the calculator to see when basically these two equations were equal. The intersection point shows you that they are equal at that time. So basically the same number of turtle nests after 31 years after 1990. Remember, we were doing 1990, so about 31 years after that would be equivalent. So that would be equivalent to the year 20